The Eiffel Tower, an engineering icon that changed the face of the modern world.
The Eiffel Tower is not only an achievement of its time, it's also a symbol of our contemporary world. Skyscrapers, tall structures wouldn't be there today if it wasn't for the Eiffel Tower.
Nothing like it had ever been built before. A totally novel design, an unprecedented height, built in record time. What made it possible? What were the secrets of Eiffel and his engineers? How did the properties of a modern material allow them to build such a unique structure? One that could rise so fast and so high.
For Eiffel, the tower is really the product of 30 years of innovation and experience.
Researchers are retracing Eiffel's career, building metal structures around the world that push the limits again and again. This is the story of a one-of-a-kind engineering adventure. Building the Eiffel Tower, right now on Nova.
Sailing a river through the heart of cities and landscapes with Viking brings you close to iconic landmarks, local life, and cultural treasures. On a river voyage, you can unpack once and travel between historic cities and charming villages, experiencing Europe on a Viking longship. Viking, exploring the world in comfort. Learn more at viking.com.
March 31st, 1889. An important day for engineer Gustave Eiffel and for France. As he raises the French flag 1,024 feet above ground, at the top of the tower that bears his name. The tallest structure in the world.
And you can imagine he was probably full of a sense of pride. Pride for himself, pride for his team who had built this monument, and pride for France, because it was the highest monument in the world which had been erected right in the heart of Paris.
Even today, the size and height of the tower is almost shocking against the Parisian skyline. So where did such a strange idea come from in the first place? Surprisingly, the concept for the Eiffel Tower did not come from Gustave Eiffel himself. In 1884, just 5 years before the tower's inauguration, two of Eiffel's best engineers, Émile Nouguier and Maurice Keckler, have an idea. What if they could build a monument for the coming World's Fair in Paris? The engineers draw the first few sketches of a unique metal pylon that could rise above the city. A tower made of iron, 1,000 feet tall. At first, their boss is unimpressed. The tower they designed would be inaccessible to visitors, and he doesn't find it attractive.
Eiffel doesn't seem interested in this idea until the Paris municipality and the French government, represented by the Minister of Commerce, Edouard Lecroix, decide to launch an unofficial appeal for ideas. It's not a competition, it's a request for projects.
A few weeks later, in-house architect Steven Silvestre adds decorative arcs to the original pylon sketch, as well as platforms for public use. As the tower becomes less of a passive landmark, but a structure people can actually use, Eiffel gets excited by the project. But many obstacles remain. Even if their design is chosen, they will need to raise millions of francs and figure out how to actually assemble such an enormous iron structure of unprecedented height. 1,000 feet tall. Today, there are countless structures that rise higher. In China, the famous Shanghai Tower is more than twice as tall, at 2,073 feet. And in Dubai, the Burj Khalifa is almost 3 times as tall, at 2,717 feet. But at the time, a 1,000-foot tower made of iron seemed like utter fantasy. Eiffel's tower is expected to be more than 4 times higher than the towers of Notre Dame, more than double the height of the Great Pyramid of Giza, and almost twice as high as the Washington Monument, at the time, the tallest human-built structure in the world at 555 feet. Since the early 19th century, several architects had been attempting to break height records, whether in France, in England, or in the United States. These lofty plans expressed the optimism and aspirations of the century, a time of relentless industrialization. But there was a reason why none of them had ever been built.
Building high, higher than the pyramids of Egypt, higher than the cathedrals in Europe, was really a goal which could be only achieved by using the modern technology provided by the Industrial Revolution. So the idea was in the air, the idea was around, but to have an idea is a good thing, but to achieve it is even better.
One of the first engineering decisions in any building is what materials to use. Eiffel knows that in order to go high, the materials must be light. Limestone, used in many Parisian buildings, is far too heavy for such a tall structure. The only viable option is iron. But in what form? At the time, Eiffel had 3 choices. The first, cast iron, a material with relatively good compressive strength, meaning it resists heavy loads. But because it contains a lot of carbon, it has poor tensile strength. Used as a girder, it is susceptible to bending or cracking under tension. Steel, by contrast, has less carbon, giving it excellent tensile strength and compressive strength. But it is costly and not yet widely available in the 1880s. Luckily, there's a third option, referred to as wrought iron. It is produced in a furnace that almost completely filters out carbon impurities. It isn't as strong as steel, but it is a highly reliable material, also with high compressive and tensile strength. It is both tough and flexible, and has the advantage of being affordable and readily available. For Eiffel and his engineers, there is no hesitation. Wrought iron is the material of choice.
Eiffel had a good confidence in this material. When you build 300 meters high tower, the highest in the world, well, you want to use a material with which you have a very strong habit of building, which is reliable.
Eiffel's confidence comes from his long experience working with wrought iron, including one of his most successful projects, the Garabie Viaduct. This is where one of Eiffel's biggest achievements still stands today. Perched 400 feet above the Truyère River, the viaduct was built in 1884. at the exact time when the project for the Eiffel Tower was first conceived. At the time, taking on a challenge of this magnitude was unprecedented.
You need to imagine that when this place was built at the end of the 19th century, there was absolutely nothing. The first step was to build a small village where the workers could be housed during the construction. Construction lasted 4 years. The first phase was devoted to the masonry and the second to the metal structure.
The engineering problem was how to build a bridge almost 2,000 feet long, 400 feet above the river.
To build this bridge, Eiffel performs an act of pure audacity. He uses an innovative technique known as cantilevering, which requires building the arch and the deck from both sides at the same time. The central part of the bridge is built using the pylons as support points. Then, cables hold the two halves of the arch until their junction at the central part, 120 meters above the river. This requires extreme precision both in fabrication and assembly of the elements. Eiffel declared that they achieved that with mathematical precision.
The construction of the Garrabee Viaduct required precise planning and fabrication. But most importantly, its success was made possible by wrought iron, a material which allowed construction of a light yet very strong structure, able to support heavy loads while resisting strong winds. This experience would prove extremely valuable. With the material chosen, the next question was how would such a structure behave aerodynamically? As a tapered, vertical structure 1,000 feet tall, the design had to withstand variable wind speeds that would change at each level along its height. Those winds were not well understood, and when calculating the tower's aerodynamics, Eiffel and his engineers only had theory to guide them. But this wind tunnel, which Eiffel built in Paris 23 years after the tower's completion, today offers a unique opportunity to understand the wind forces he and his engineers had tried to calculate.
At the time of the Eiffel Tower project, the highest structure was the Washington Monument, which is half the size of the Eiffel Tower and built in masonry. That construction took several decades as the ground underneath kept sinking. Eiffel's idea was to use a completely different material to switch to metals, which solved the weight issue. But then they faced a new problem: wind.
Here, physicist Benoit Romo compares the effects of wind on two models: a straight tower on one side and the Eiffel Tower on the other.
So here we have a wind speed of 10 miles per hour. We see very clearly that the straight tower is bending much more than the Eiffel Tower, which shows its higher rigidity and wind resistance, even though they're the same height and have the same quantity of materials.
So why does the Eiffel Tower resist wind so much more effectively? Iron is a flexible material, so the great height of the structure makes it vulnerable to large wind forces. But with this unusual shape, the force of the wind and of the tower's own weight naturally directs the resulting force downward, following the curves of the tower.
This is the best shape imaginable for wind resistance. It has the elegance of a mathematical solution. It's truly optimal.
And history has proven that this entirely novel design was the right one to stand the test of time. During the Great Storm of 1999, a record-breaking wind speed of 134 miles per hour was recorded at the top, and the tower stood strong. Eiffel has just received good news. After months of negotiations, his Iron Tower has won the official competition for the World's Fair Gateway Monument, and construction has finally been given the go-ahead. The site will be on the bank of the Seine River, where it will be allowed to stand for 20 years.
So the World Fair had a very important signification in the time, politically, of course, to show one country's strength, but also to show what the industry could deliver and how everyday life could be changed by these new products.
For Eiffel's company, it's the beginning of a race against time. A race that will test all the talent and skill of the country's best engineers to produce sketches for each of the tower's 18,038 pieces, and a plan to assemble more than 8,000 tons of iron through summer and winter, rain and snow. After months of preparation, the tower's construction can finally begin. But being so close to the river means the soil is soaked with water. How to build the foundation for the world's tallest building on such potentially unstable terrain? Once again, Eiffel looks to his own experience for the solution. This bridge was inaugurated in 1860. It's the first major iron structure Gustave Eiffel worked on as a construction manager. The idea was to build a railway bridge across the wide and turbulent Garonne River.
For the young Gustave Eiffel, this bridge is the chance of a lifetime. He knows he's competing with another engineer who's building a similar bridge in Strasbourg, and he really needs to do better, faster, and cheaper. So he decides to standardize his parts. The construction gets more efficient, less costly, and he ends up winning the race, building a decidedly modern bridge.
The biggest obstacle was building the piers, or support structures anchored in the river. The question was, how do you build a foundation 80 feet underwater?
Eiffel implements a new technique discovered through his first employer, Charles Nepveu. It involves large cast iron tubes, 3.6 meters in diameter. The lower part rests on the bottom level, and the upper part is above the water level. It is divided into 3 chambers. The lower chamber is pressurized, constantly fed by compressed air, and it allows workers to work on a dry bed. The middle section is a decompression SAS, and the upper section is open air to allow evacuation of the rubble. This innovative technique, which ensured a fast completion of the foundations, is a key factor in the construction of the Eiffel Tower.
In the middle of the Paris winter, the work begins. Soon, around 500 workers gather to dig the foundation of the tower's north and west pillars, the nearest to the Seine. Piece by piece, just like in Bordeaux, large watertight metal boxes are assembled, which will form the pressurized chambers, or caissons, to allow construction of the foundation to be protected from flooding. Then the project encounters a serious problem.
When the pressurized air chambers come into use, workers develop an unknown illness. They report tingling sensations, bleeding, difficulty breathing, and partial paralysis. No one understands the cause of this ailment, nor the importance of making decompression stops when coming back to the surface.
Today, the illness is known as the Benz, or caisson disease. Inside the caisson, much like underwater divers, workers breathe air at a high pressure. But if they return to the surface too quickly, and the pressure drops rapidly as a result, nitrogen bubbles can form in their blood, causing decompression sickness. Nobody understands what is happening. Even the government is concerned about the potential danger.
In April 1887, the Minister of Commerce and Industry decides to go down himself into the foundations, and he comes back up alive.
It was a demonstration that the caisson was not so harmful and it was not a problem which could delay the construction of the tower.
Despite the discomfort, work resumes until the piers are in place. Soon, solid masonry rises from the foundations to support the metal structures at the bottom of the tower. Now they can begin the ironwork. One by one, the fabricators melt, cut, trim, and drill the future tower's 18,038 pieces to exact specifications. For the assembly method to work, millimeter precision is absolutely crucial from start to finish.
The Eiffel Tower is kind of complex, but when you look at it closely, it's only made with sections in the shape of T, L, U. So you can see that the very simple parts used in the Eiffel Tower combined in a complex structure can achieve the highest monument in the world.
Horse-drawn carts deliver the prefabricated components to the construction site on the Champ de Mars. 6 months after the start of construction, 4 54-degree inclined pillars, each composed of 4 large assembled tubes called trusses, rise from the ground. So far, all the pieces fit together as designed. But how do the engineers ensure that nothing moves out of place? Once more, Eiffel calls on lessons learned building another famous structure. In these Parisian workshops, France built another monument which remains just as iconic: the Statue of Liberty. And under its skin lies one of the secrets to the Eiffel Tower's structural strength. In 1870, renowned French sculptor Auguste Bartholdi imagines a 300-foot-high statue in the form of a woman celebrating the signing of the U.S. Declaration of Independence.
Certainly, monumentality has a long history prior to the 19th century. But the notion of creating the colossal is so profoundly a modern ambition. And Bartholdi began his thoughts about the Statue of Liberty in Egypt. He was making terracotta little models, but when it's about realizing he has to turn sculpture into a modern phenomenon, the reason it can be that gigantic is that it's hollow.
Tall and in the shape of a person, yet hollow. How does this structure hold together? It's 6 a.m. in New York City. Before thousands of visitors arrive, Ranger Matt Hausch leads the way on an exclusive tour into the heart of the statue. The similarities with the Eiffel Tower are easy to spot.
what's most impressive about the interior of the Statue of Liberty is how all of this iron and steel works together to hold her over 300 feet above New York Harbor. Over 100 years of wind and rain, and she still stands because of this interior structure.
After the teams riveted together the internal structure's iron beams, they next installed a secondary structure made out of hundreds of iron bars. On top of these bars, they attached the copper skin, piece by piece. And the secret to these layers holding together is in one simple but incredibly effective solution: rivets.
The inside of the Statue of Liberty can be a disorienting place. But what you're seeing are hundreds of copper plates. So that's the dark metal that you see all along the interior here. That's her skin. And those copper plates were all riveted together with thousands of little copper rivets. But the copper skin has to be held up. So we can see there are thousands of steel bars connect the copper plates to the secondary iron bars, and all of those iron bars connect back here to these iron pylons.
Building high, building light, and building strong. Mastering the art of riveting for the Statue of Liberty would prove crucial for years to come. Today, rivets are not common. High-strength bolts are more often used to attach large steel components. But in Gonesse, north of Paris, a few highly skilled workers still practice the efficient assembly technique of riveting.
Faudrait qu'on avance par là. Okay.
In this workshop, Eiffel-style beams are sometimes produced to restore old structures. These rivets are pins, but unlike bolts, they don't have threads or nuts. Instead, they are heated, softened, and custom fit into place. The first step is for a worker to heat the rivet in a small furnace, and then place it in the assembly hole. A worker holds the rivet's head in place, while another uses a hammer to crush the emerging end. As it cools, the rivet retracts between the two pieces of steel. The technique might look straightforward, but during the construction of the tower, teams of 4 riveters worked up to 12 hours per day in highly dangerous conditions. On average, workers installed fewer than 1,700 rivets each day, out of a total of 2.5 million.
It was really a long, a bit tedious process, but very strong, which could last, of course, for a long time. And if the tower is still there today, it's also because its way of assembling its parts was very efficient.
Hundreds of workers are now giving their all to meet the deadline. And the construction progress is impressive, with the metallic structure rising fast to the incessant beat of hammers. As the tower grows, lifting thousands of tons of iron to greater and greater heights becomes increasingly difficult. But Eiffel has an innovative solution: placing mobile steam-powered cranes attached to each of the tower's legs.
These 15-ton cranes installed on sloping and then vertical rails that will later be reused by the elevators drive the progress of the building site. Eiffel's cranes are steerable, have a range up to 12 meters and a lifting capacity of 3 tons. They will contribute to the success of this colossal project.
The legs of the tower are now rising above the Parisian skyline. So far, no major disasters. None of the workers have died, the foundations are not sinking, and the structure stands strong. But it's still early days. The real test will come during the next stage, joining the legs and constructing the tower's second-level platform to support the huge tower that will rise above. Turning hand-drawn designs into forged pieces and then finally bringing them together to connect perfectly. It's a pivotal moment for the engineers. But how to ensure the tower and the platform will remain level and true? Once again, Eiffel and his team prove extremely inventive.
Eiffel designed two devices, sandboxes, an ancient technique used by the Egyptians, and hydraulic jacks to help level out the position of the piles. To push them up slightly, just to adjust the final position and the junction of the four pillars. In addition, sandboxes were placed at the top of the scaffolding between the box girders, and to adjust them, just simply drill a hole and let the sand flow out. By combining sandboxes and hydraulic jacks, the exact position of the holes drilled in the horizontal girders and in the box girders to adjust precisely the first platform. And this was really the crucial event of the construction of the tower.
Finally, the main platform's last rivet is set. After years of work, months of uncertainty, the construction's most delicate step is now complete. The tower finally stands on its own, aligned to support what will now rise above it. The most difficult phase has been completed, but there is still just over a year left to build about 700 feet. As winter wears on, Eiffel hits a rough patch. His construction has been hindered by the weather and tarnished by considerable backlash.
You have a very strong criticism by eminent artists of the time, writers like Maupassant, architects like Charles Garnier, the architect of the new opera in Paris, intimately. I'm sure it was a bit shock or maybe a harm for him not to be felt understood as really doing something exceptional for its time.
Eiffel is determined to turn public opinion around. His business may be engineering, but he also understands the importance of public relations. A few months later, Eiffel has an unusual idea. Organize a special banquet at the tower's second level. He's hoping everyone will finally understand that this project isn't just an engineering challenge. It's a unique and timeless work of art. Right in the middle of the construction site, tables have been set to welcome a select crew of journalists. And it works. According to the New York Herald, the guests are dazzled. It appears that the road to success is clear, at least for now. Step by step, the construction continues. Following the second floor, the tower's third floor comes together, 377 feet above the ground. These X-shaped structures may appear decorative, but they serve an important function. Why include this feature? The answer comes down to the fundamentals of structural engineering. When held by a single diagonal, a structure is vulnerable to the horizontal force of the wind, depending on where it comes from. But with two diagonals, the structure resists horizontal force more effectively. As one cross brace is pushed or pulled, the other resists in the opposite direction, maintaining the structure's stability.
In all Eiffel structures, you can find these cross-shaped sections to brace the elements, vertical and horizontal. Very typical of Eiffel construction, but also of the iron construction of its time.
This principle was long used in wood construction, but Eiffel was the first one who used it extensively in metal construction. It became a key to his method, whether in the tower, in the Garabie Viaduct, or the Statue of Liberty. Since the start of the construction, Eiffel knows that time pressure is high. So he takes pains to treat the workers well.
Carpenters were the best paid, earning 80 cents an hour. Fitters and riveters, 70 cents an hour. And laborers, known as the moose, 60 cents an hour. They were paid almost twice as much as workers on other Parisian construction sites of the time.
But as the structure narrows towards the top, the workers go on strike, and Eiffel's busy building site grinds to a halt.
They work at ever greater heights. In response to their complaints about this danger, Eiffel replies that there's no more danger at 1,000 feet than at 100 feet. So he tells his workers to get back to work, warning them that if they don't punch in the next morning, they'll be fired.
When only 27 workers show up the following morning, Eiffel quickly does the math. If the strike continues, even just for a few days, the tower might not be completed on time for the World's Fair.
If the tower would be completed after the opening of the exhibition, it would be a major failure for him, for himself, but also for France.
Eiffel gives in. He offers the workers a gradual increase of 5 cents a month until December. And for those who climb the highest, he adds a 100 franc bonus upon completion of the work, plus warm clothes to face the winter.
By the time construction begins again, the deadline for completion looms. Following the end of the strike, which lasted a week, the tower reaches 557 feet, becoming the tallest structure on Earth. From now on, progress will be faster. The structure is thinner at the top and requires fewer parts to assemble. The tower now grows by more than 3 feet each day. By March 15, 1889, the fourth upper level is almost complete. But there is still much left to do. Painting the tower, setting up the lighthouse and the lighting system, and last but not least, installing the elevator trolleys. From the start, the city's specifications were clear. If the tower was to be 1,000 feet high, it should be accessible to the public. And that meant elevators. But how to power them, especially in such a tall and unusually shaped structure? In this space, located right below one of the tower's pillars, Eiffel built a one-of-a-kind elevator based on the same technology he used to level the tower: hydraulic pressure.
In 1889, water pressure was already used to move the elevators.
Behind this complex set of tubes is a somewhat simple idea. Water is pressured from a first cylinder into a second one. This generates a big push at the other end, where the pressure is released. This move is translated into a series of pulleys that stretch cables to allow the elevator to move up and down.
From 1900 to 1986, there was a person underneath the elevators in the pilot's cabin. And this person had a big steering wheel. When the pilot was steering the elevator, the passengers depended on the smoothness of his movements. If he opened up the throttle quickly, the elevator would shoot up.
But Eiffel's promise was to take visitors to the tower's very top. For that purpose, he built another set of elevators between the third and fourth floors.
An ingenious system of two cabins connected by a cable ensures the transport to the top thanks to an 80 meters coarse hydraulic piston. When the piston pushes up the lower cabin up to 80 meters, the upper cabin goes down 80 meters. At halfway, visitors pass from one cabin to another on a platform which offers an impressive view over Paris. And then the other cabin continues its ascent.
Today, the tower's elevators remain a testament to Eiffel's bold sense of innovation. But they weren't ready for the opening of the World's Fair, so the first visitors would have to climb to the top on foot. Just over a month before the World's Fair inauguration, the tower's construction is finally complete. And it has officially become the tallest building in the world. For Eiffel and his team, this success is the result of more than 5 years of work. But the monument would be more than just impressive. It would be striking, even colorful. Since its construction, the Eiffel Tower has received 19 layers of paint to protect it from corrosion, an average of once every 7 years. Today's Eiffel Tower has a different color than it did on opening day. To better understand the history of the tower's coloration, heritage restorers Claire Dondrel and Annick Texier are examining the layers of pigment that cover the iron.
Here's my incision, which should be pretty good. Now I'll sand it. On this beveled cut I just made, I place my device, which is very small and very precious. It's a digital field microscope connected to my computer, and Annick checks the image from the microscope. Looks good.
Yeah, you're pretty much in the middle there. You just have to focus.
These photos will be used to document the history of the tower's painting.
We see all the stratigraphic layers, meaning all the colored layers on the metal of the tower. Here we see black with metal chips. On this metal, we can see a bright red layer. This is Eiffel's first preparation layer.
When it was constructed.
At that time, red was the protection layer. It was applied in the workshop as the metal parts were manufactured and added as the tower was being assembled.
The conclusions are surprising. From one painting campaign to the next, the tower's colors have changed several times. From red at the time of the World's Fair to much darker today. But now the tower is being repainted again, in keeping with its color of 1907, when its long-term survival was settled. Covering every inch of the structure, a team of acrobatic painters follow the same methods as their predecessors, using tools such as the guipon, an angled brush similar to those used by the Eiffel workers. It took 66 tons of paint to complete the tower's 19th paint job. It is a day of celebration for Parisians and for thousands of tourists who join them from across the globe. After a 2-year-long race against the clock, the long-awaited World's Fair of 1889 is officially open. At this climactic moment, Gustave Eiffel is surrounded by his engineers, now close friends, Émile Nouguier and Maurice Kekla. Although the tower will only go by Eiffel's name, it is the team's accomplishment and masterpiece. The product of years of collaboration with a common goal: to push boundaries and explore uncharted territory.
Eiffel is proud for himself, but he's also proud for his team. Not only him, but his own company can be really proud of this success.
As the World's Fair gateway, the Eiffel Tower is a huge success. From the tower's heights, visitors from all over the world discover Paris from a completely new vantage point. On the evening of May 6, 1889, as a grand celebration unfolds, Eiffel is riding high. But the tower's story is far from over. Eiffel is worried about the monument's future. He knows it has only about a decade left before its lease expires. After that, the tower's fate is uncertain.
If the tower had to be destroyed after the 20 years concession which he had, he would have been like an orphan, losing his major structure, losing the structure which made him famous, and probably it was for him unacceptable.
In 1898, Eiffel is eager to find a scientific justification to keep the tower alive. Soon, he invites 2 engineers to carry out wireless radio transmission experiments from the top of the tower. The experiment proves that the height of the tower can extend transmission range. But that confirmation alone is not enough to save the tower. As wireless telegraphy is rapidly developing, Eiffel realizes the tower could be an invaluable tool for communication. And in 1904, the monument is equipped with a cutting-edge antenna, allowing the French army a reliable radio link with its defense posts 248 miles away. The tower proves its strategic importance. And in 1909, Eiffel finally receives the news he was hoping for. The tower's lease is renewed. It will not be destroyed.
Then he could be relieved when the concession he had was extended to 70 years. And for him, it's really something to be proud of, to be sure that the tower would remain. It was in the beginning of the 20th century one of his main objectives.
An emblem of the 19th century and the Industrial Revolution. The Eiffel Tower ushered in the age of skyscrapers, like the Chrysler Building, completed in 1930, and the Empire State Building, completed in 1931.
The Eiffel Tower is not only an achievement of its time, it's also a symbol of our contemporary world. Skyscrapers, tall structures wouldn't be there today if it wasn't for the Eiffel Tower.
Standing through the roaring 20s, where it introduced radio to Parisians for the very first time. Enduring 2 world wars, where it was used as a one-of-a-kind antenna. Bringing major contributions to science and technology. The tower steadily claimed its place as a timeless icon and a crucial part of French identity. Today, the Eiffel Tower continues reinventing itself. In 2000, 20,000 strobing lights were placed directly on the tower's structure. And 22 years later, a team of specialists installed a new antenna to set up Paris's new digital radio network.
Although it is very representative of the 19th century, the Eiffel Tower still stands today as a source of inspiration for engineers, architects, builders in the world.
A universal icon of Paris and France. The Eiffel Tower continues to stand the test of time, inspiring those who see her to dream bigger and bigger.